Okay, good afternoon. Thanks for joining, and thanks for the introduction. So I'll talk about something that I've been interested in for a number of years now, which is using the stuff that people leave online in order to learn about health and medicine. Now, first we should say what is internet data, and I think there it's roughly speaking whatever people leave online as they do their business. You may think of this as that famous Supreme Court statement, I know it when I see it. And here are a few examples of the ways that people have used internet data to learn about health, from using genealogy data to study things related to cancer mutations, through using pictures on social media, in this case on Twitter, to infer people's BMI and therefore learn something about their health. And also using, maybe this is perhaps the first paper in this line of work, which is using search data to learn about influenza rates. And within this area of research, I think by now we can see three main areas where this kind of research can do or can contribute something that other forms of medical data cannot. And these three things are where people extensively interact online, meaning when they go online to find something or when they go online to study something. When people have a difficulty reporting, because what we are asking them to report in order to collect our data is something that they find difficult, either because it's embarrassing or more frequently because they don't realize that there is an association, but we can make it for them. And the last one is when actually internet data is a more sensitive sensor than what current medical sensing provides. And I'll give you examples of each. For the first one, I'll talk a little bit about our work on trying to make headway into suicide prevention. In the second one, I'll talk about detection of faulty medicines. Again, this will be an example of something that people find difficult to report because they don't realize that there is something to report there. And the last one is when we want to monitor influenza-like illnesses. I'll talk about two of them, one about actual influenza, the other is about another virus that's very similar. So without further ado, let me begin with the first one about suicide prevention efforts. This is a book called The Sorrows of Young Werther. It was published in the late 18th century. And it talks about, it's this romance, it talks about young Werther whose love does not reciprocate his love, and therefore he goes to somewhere in Austria, I believe, and he kills himself by suicide. And I specifically use these words, and you'll understand why in a minute. But people noticed that shortly after this book was published, there were quite a few people who followed the example of young Werther. And how do we know that they followed his example? Because he wears very specific clothes, according to the book, when he goes and kills himself, and he does it in a very specific way. And people noticed that across Europe, there were multiple cases of these kinds of suicides. And so this idea of copycat suicides, when people hear about somebody killing themselves and then going and doing something similar, is called the Werther effect. And it's been shown on a population level when there's a famous suicide. Soon after there's a rise in the number of suicides, but we want to see whether we can do something about this. And what we want to be able to say is what in the publication of the information about suicides causes other people to go and try to do this themselves. So how do we approach this? The first thing we have to do is we have to find all those people who ask how to commit suicide just before they do it, and then see if we can go back in time and realize what caused them to go and make this awful choice. And so we're using search data here, and we're dividing this into two stages. The first stage is to say, if there was a news article that was published somewhere, what's the likelihood that a person asking how to commit suicide has read it? And we can do this because we know the relationship between where people live and what they read. And in these two graphs, you can see the distribution of CNN viewers versus the Jacksonville Times, which is quite limited in Jacksonville, Florida, obviously. So that's one part of exposure. The other part is how long between the publication of a news article and when a person asked, how do I commit suicide? And again, there's a very typical curve here. The horizontal axis here is time in days. Time 0 is when an article was published talking about somebody killing themselves. And then the distribution you see here is when people actually read that article. So now, when somebody asks how to commit suicide, we can say, what's the likelihood that they were exposed to any one of these news articles? We can break these news articles into words, and then we can build a predictive model that will take the words of these articles and say how many people who read these words are likely to ask, how do I commit suicide? This very actionable query. And you'd be surprised how many people actually ask these kinds of things. Turns out that it's not a very difficult question to answer if you take those words. And if we look at the accuracy, these are the areas under curve. For suicide, just look at the first line, we get almost perfect score. So give me the text of a news article and I will be able to tell you how many people will ask how to commit suicide after being exposed to that article. And that's useful because then you can actually change the words in the article to make them less troublesome. And in fact, the CDC has guidelines for journalists that tell them how to report about suicide. For example, you would have noticed that I didn't say took his life into his own hands because that is known to be a very triggering phrase versus he killed himself by suicide, which drives many fewer people to commit suicide. The other 4 lines here are more positive aspects. For example, if somebody is reported to have been diagnosed with AIDS, how many people will ask, how do I test myself? Or where do I test myself? Or when Angelina Jolie talked about her double mastectomy, how many women asked, should I be tested? Where am I tested? This is the line talking about mastectomies. Again, the prediction is not as good, but it's still quite good. And so we can give this tool to journalists and allow them to get at the more impactful papers or the articles in a way that was not possible before. So that's one example. The other example I wanted to give was that of detection of faulty medicines. A number of years ago, perhaps 6 or 7 years ago, we showed that using search data, we could detect side effects of drugs. The basic idea was very simple. Somebody goes out of the doctor's, he asks about the drug that was just prescribed to them, and then sometime later they may ask about a side effect. They may not even realize that one is caused by the other, but we can do it for them because we see so many people. So that was a few years ago, and then we realized there's another problem that is worth looking into. And this is of drug recalls. So we're not talking here about when an entire drug is discovered to be harmful, something like thalidomide or things like that, but when there's a specific batch that was faulty. Specific batches are usually sold in a single state or a few states across the US, and sometimes they're faulty. In this case, it's the injection mechanism of the EpiPen in a specific batch that was found to be defective. And so they have to be recalled. And interestingly, there are quite a few recalls. This is recalls in the US, they're divided by classes, meaning how serious are these recalls, but you'll notice that there are hundreds every year. So we wanted to see whether search data would be able to tell us that there is going to be a recall because people start searching for this. If you pose it in this way, it's quite a simple problem. You look at how many people ask about each drug that you're interested in over time. And then you're trying to say, is this spike indicative of a pending recall? Meaning people start searching for this drug more often. They may not even realize it's something wrong, but they feel that something is not exactly as it should be, and so they search for it. And so, of course, what you would do is you would extract some attributes and try to predict ahead. The problem from a data science point of view is in 2015, there were about 4,000 recalls, 3,700 recalls, but we have about 6,000 drugs that the FDA tracks. And we have 50 states and 365 days a year. So in fact, this translates into a problem which is highly imbalanced, only about 0.2% positive samples. And so it needs some more machinery. In this case, what we did was we first clustered the data, the time series data, then we had a set of classifiers each for each one of these clusters, and then used max pooling. But if you do this, it turns out that indeed this hypothesis that people start searching for a drug when they realize something is wrong, even when they don't realize that they should report it, actually holds water. So this is a performance curve called the lift curve. It shows at each given percentage on the horizontal axis how many more drugs would we detect that are actually faulty compared to just randomly sampling the population. So for example, if we look here, say if you had a budget every day to sample 2% of the drugs on the market, if you used this classifier, you would find 6 times as many faulty drugs as a random sample. And you can go back in time to see how early could you have detected these faulty batches. And this is this graph. So this shows going back as many as 2 months, as much as 2 months, how well would you have predicted? And so we could actually detect these drugs before they are recalled. There's an interesting side note here, which is after our original work on adverse reactions, we talked to a few drug companies. We actually worked with them on these problems. And they sort of, in passing, mentioned this problem of detecting recalls, but they wouldn't give us the data to work with. And so this work had to wait a few years before the FDA started putting out data on recalls, which we could cross-join with the search data. Okay. And the final example, examples which I'll talk about, are related to cases where internet data is actually a better sensor than what you would get using sort of normal or traditional medical information. And the poster child here are influenza-like illnesses. Usually if you catch the flu, you think it's influenza. Actually, in most cases, it's not. So we call them influenza-like illnesses. Now, why are we interested in those conditions? So here's a graphic example. If we have about 1 million people in a given population, on a normal year of the flu, about 200,000 will carry the virus. Of those 200,000, about 5,000 will seek medical attention. So they'll go to a hospital or they'll go to the family physician, and therefore they will make themselves known to the medical system. So you see there's a huge gap between the 200,000 and the 5,000. And of course those 5,000 are not a random sample of the population, right? These are the elderly, these are the very young, these are the people at risk, which is good, but it's not good for us if we want to track the flu. And I should mention that of those 5,000 people, about 100 people will die. This is your normal flu. This is not the Spanish flu of 1918. However, there's a lot of work going into influenza monitoring specifically to detect if it's not the killer flu, if it's not the seasonal one, but the one that will kill so many more people than the normal year. Now, why is internet data useful? It's useful because about 75,000 people, according to our estimates, will go on social media and say, oh, I have the flu and I'm feeling so bad, or will go on Bing or Google and ask, what are the remedies for the flu? And so we have many more people out of those 200,000 people that we see online than the medical system does. And these 75,000 people are arguably a much more balanced sample than what the medical system does. So I'm not going to talk about monitoring the flu. There's a bunch of papers on that, probably hundreds of papers. I want to talk about 2 other, perhaps more interesting cases. A few years ago, the British Health Ministry decided to vaccinate children against the flu. The idea was very simple. Nobody cares if a child has the flu, if they're, I'm talking about primary school children. The thing is, if a child has the flu, they stay at home, and their parents call their grandparents to stay with them. And then the grandparents catch the flu, and they die. So the idea was, if you vaccinate the children, you may prevent that from happening. And indeed, if between the time that this article was published and earlier last year, you may have seen this article, or if you have second grade children of your own, you'll know that they were vaccinated against the flu. And partly that was my fault. Why? Because going back to this article, the British Health Ministry did something very nice. They did a random experiment. They chose 7 cities, they vaccinated the children there, and they didn't vaccinate them in the rest of England. And then they thought that they would check how many hospitalizations there were in those 7 versus the rest of the country. Turns out that this is not a sensitive measure of influenza. So what they did was they came to our colleagues at University College London and to us, and we used Bing data and Twitter data to show that actually there was a reduction of approximately 25 to 30% in the number of cases in those 7 cities compared to what you would expect in the rest of the country. To do this, we used some algorithms that were originally developed for local advertising, which I found interesting because finally somebody does use something beneficial with Google, with advertising algorithms. So that was 1 year. The following year, they did a bigger test. And the bigger test, this is England, they vaccinated in some areas only primary school children, in others secondary school children, and in some areas both. And then they again came to us and asked if we could measure if this was effective. Interestingly, in secondary schools, we saw no difference, which kind of makes sense because when you have a 12 grade student, you don't call the grandparents to take care of them. But still, in the primary school children, we did see a reduction. Following this evidence and others, the British Health Ministry is going to roll this out in the entire country. And as you saw in Israel, they started doing this first with second grade children and hopefully next year with a larger group of children. And finally, this is another example, which I find interesting from a data science point of view. Here we're talking about RSV. It's a similar virus to influenza. It has slightly different parameters, but think of this as another kind of influenza. And this has been tracked in the US in a few of the states, which you see here marked in brown over several years. And in those states, we can show very nicely that there is good correlation between the number of cases, which you see here over 10 years or so, and the searches for symptoms related to RSV. So that's good. But we want to be able to say something about the rest of the country, and this is a very typical problem, where you have good data for some of the country, but no data for the rest of the country, or no good data at least. And so what we did here was we used domain adaptation. We learned from those countries where we had good data, and then we domain adapted our models to the rest of the country. And the results were actually quite good. The color code here is the correlation between actual virus loads and our predicted loads. And if you want the histogram, it's over here. So you see in most states, we can actually get very good models by just domain adapting them. Why would you want to do this beyond just knowing how many people are sick? So for example, here the color codes represent when in the season does RSV peak. And darker colors of green mean later in the season. What basically you see is the RSV starting from Florida over here on the right-hand side and going to the northwest. And this was validated in other studies as well, but we can actually predict very nicely. If you tell us when RSV started, we will tell you when it's going to peak in every other state, and that's actually very useful information, apparently. So to summarize, I believe that, or I hope that I've made you excited about this idea of using behavioral data from the internet to provide insights about disease. We know, or we have a rough idea where this can be useful, and I didn't talk about a lot of other studies that we and others have done in this space, which are also, I think, very exciting. Things like pre-screening for cancer by looking at people's queries, discovering other risk factors for disease, again, by looking at what people did just prior to when they developed a condition, helping people with anorexia and other eating disorders to recover by using some very basic interventions of posting ads, basically, and measuring the effects of health policy decisions. All of these things are things that we've done in the recent past, and if you're interested, I urge you to join us. And I'll finish with advertising for myself. If you're interested in this field, this book of mine came early last year, and it talks about all the wonderful ways that people have been using internet data for health. Thank you very much.